let's talk about some first order system identification from a step response. So here we are going to do system identification of integrators and differentiators. We'll do the integrators first. So in Desmos, I programmed the step function and it's red, and really it's just the sign function um, scale to get the unit step. And then the square wave is actually a sine wave inside the step function here, which then makes this oscillating structure. Desmos has some sharp transitions, and so you won't see the full square wave, which is in green. So the first response is the step response of an integrator, which you're basically integrating this straight line and you're based on the scale factor, or you're 1 over RC, and so that's what we get for the blue line. And so if your scale factor is negative, the slope is negative. If it's positive, it's positive. So if you're trying to test an integrator, just put in you can put in a step and measure the slope. Now, of course, at some point your ramp is going to go beyond the limits of your testing equipment, so you can use a square wave like I've got here, so that the slope will come up and then the slope will come down. Slope comes up, and you just have to find the slope of this line to find the scale constant for your integrator. Now, for a differentiator, I have actually this ramp, which is input to the integrator, and it's just taking the slope. So when the slope is positive, this black line is positive. When it's negative, this black line is negative. And so really that's just the two simplest first order systems are the integrator and the differentiator. Now let's look at the high and low pass filters. And actually, even though we're talking about this transient step response, I'm going to start with the frequency response. And so we have the Bode plot of a low pass filter, the magnitude in red, phase in blue, and the gain is DC gain is 0 dB, so that translates to 1. And as we move this corner frequency back and forth, this is when omega naught gets smaller and smaller. This is when it gets bigger and bigger. The smaller omega naught, the more of this straight line we get, and the more it acts like an integrator. The bigger omega naught, the less it acts like an integrator. And we can see how that plays out with our transient response. So the red is the step response of the low pass filter, and this purple is the step response of a high pass filter. And here we have, it's programmed as A, but it's really omega naught. And as it gets really, really small, it acts more like an integrator. And look, the step response in this area looks very ramp-like. Right? Well, that's the integration of a step, is a ramp. So you can see that when omega naught is really small, low pass filters act like integrators. And when omega naught is really large, it charges up quite quickly, and it's very closely matching the step response, which there I can turn it on, and now I can turn it off. Now let's look at the high pass. Magnitude in red, phase in blue. Now as omega naught gets smaller, or let's do larger, we get this straight line up, which is acts like a differentiator. So as omega naught is getting bigger, it's acting more like a differentiator. As it's getting smaller, it's passing more and more of the frequency content. Now this is opposite to the low pass filter, that when omega naught gets bigger, it passes more of the signal, and when it gets smaller, it acts more like an integrator. With the high pass, the bigger it gets, the more it acts like a differentiator, and the smaller it gets, the more it passes the signal. Now let's go back and see how that plays out in the transient response. So right here, omega naught is large, and it's taking a long time for the high pass filter to discharge. Right, so it's passing more of that lower frequency content, and as we make omega naught large, it's acting more like a differentiator, and which is really detecting that edge of the step response. Something to consider is that look, the low pass goes from low to high, and the high pass goes from high to low. But in the Bodie plot, right, it goes the low pass starts off high and then goes low, and in the high pass it starts off low and then goes high. So these the Bodie, the frequency response, and the um, transient response, they kind of go in opposite directions. But how do we define the system? Well, we know that there's an exponential decay. How fast is the exponential decay? Find omega naught. How do we do that? Just find 5 tau. In this case, we could call it 3 seconds. Take 3, divide it by 5, and that would give you us tau. And then 1 over that would give us omega naught. Same thing with the high pass. All right, we could say, all right, it's taking 6 or maybe 7 seconds. Or let's change it to where it's taking, let's call it 3 seconds. Take 3 divided by 5, that gives you tau. 1 over tau gives you omega naught. What is the DC gain? Well, if it's a unit step response, the low pass filter will eventually pass that DC of the step, right? So the green line or the red line divided by the green line is going to be 1, so the gain is 1. For the high pass, we have to look at the right here at the edge where it starts, and it's passing that change to 1 perfectly. So first order, low passes go from low to high because notice it's passing the DC. High passes go from high to low because it's passing the edge and attenuating the DC. And then to summarize, find the AC gain for the low pass when it settles to its final value. Find the AC gain of the high pass when whatever value it starts at, but they both, in this case, the way I've drawn it, they both have the same tau. Find how long it takes to discharge, divide that time by 5, take the inverse, and that's your omega naught. And there you have it. You have identified your low and high pass filters.